Okay, so now we're going to switch gears just a little bit and talk about graphical methods for sizing reactors. So when we do that, we use a Levenspiel, or one way to do that is to use a Levenspiel or inverse rate plot. So these plots are typically used for visualizing CSTR and PFR volumes needed to achieve a certain conversion for a reaction. And they can also be helpful in reactor sequencing. So how this works, someone goes into the lab, the chemistry lab, for example, and a bench scale experiment. So something that could be carried out on a bench top. So a small vessel for your reactor. So not an industrially sized reactor. Someone will learn the chemistry, so the rate law, of a particular reaction. So they'll run the reaction and they'll learn how the rate varies as a function of conversion. And they'll make a plot of that. And we can use those plots to provide us with initial estimates about how we should, or what types of reactors we should use for a reaction, or how we should sequence reactors. Now, this information, it gives an estimate. So it doesn't give the full picture. To give the full picture and to scale up for an industrial reaction, we'd actually have to write out the reactor design equations. But this method provides a nice way to look at the reaction and how it's proceeding and come up with a first pass at how to design a reactor. So an example of a Levenspiel or inverse rate plot, basically what that is I have a graph. Ooh, that's terrible. And on this axis, I plot the quantity FA naught divided by minus RA. So the inlet flow rate of A divided by the rate of consumption of A. So A is a reactant. And I plot that against the conversion. And so usually the plot looks, or a lot of times the plot looks something like this. So it increases as the conversion increases. So the reason for that, if I think about what this graph entails, if I increase the conversion, and of A, and A is a reactant, then in that case I'm decreasing the concentration of A. So if we have an example, or if we have the case where the rate of A is equal to a rate constant times the concentration of A raised to some power, where n is a positive number, then that means that as the concentration goes down, so as the conversion goes up, then the rate also is going to go down. So the more A that reacts away, the lower the concentration is. The lower the concentration, the smaller the rate. So in other words, the rate gets smaller. And hence, 1 divided by the rate gets larger. So that's why you see this behavior here. As conversion goes up, the rate gets smaller, and hence the inverse rate gets larger. So that's essentially what is meant by a Levenspiel or inverse rate plot. So how do we use these to size reactors? So we want to use a plot like this, and we're going to show how to size both a PFR and a CSTR using a plot like this. So let's think first about the PFR. It's actually a little conceptually easier than the CSTR. So thinking about the mole balance, the PFR mole balance that we just derived, so dXA dV is equal to minus RA, so rate of consumption of A divided by FA naught. So if we wanted to get the volume of a CSTR to carry out some reaction with some kinetics and to some conversion, what would we do? What are the mechanics of doing that? So what we would do is take this differential equation and separate it. So RA is a function of x, so we'd group that with the dxa term over here, and we'd move the dv term over. And in this case, we want to isolate v by its side, so we're going to also move all of the constants over with x. So v would end up being fa naught integral of dxa divided by the rate of consumption of A. Or if we wanted to, we could move this term inside here. We don't have to, it is a constant, but we can. So what do you notice about this integral here? How does this relate to our Levenspiel plot? So if we go back up to what our Levenspiel plot looks like, this is a plot of fa naught divided by RA plotted against XA. So the PFR volume is essentially the area under that curve. So here, let's fill in these notes. RA is a function of XA. Hence, the PFR volume is curve. So if I draw that out, I have fa naught. I have XA. And I have some trend. And I want to estimate the volume of a reactor to achieve some conversion. So say I want to estimate the conversion, this some value of conversion here. The PFR volume is going to be the area under this curve. So if I take that integral, or maybe I do some sort of a summing technique to numerically get the area under that curve, that is going to give me my PFR volume. So what about the CSTR? How do I get the volume of a CSTR from the Levenspiel plot? So the CSTR mole balance looks like this. B equals to fa naught times XA divided by the rate of consumption of A. And I kind of want to organize this now so that it looks like a Levenspiel formula. So I'm going to do that. Basically, I'm just going to group terms. So over here, I would have fa naught divided by minus RA, because that's the way it's grouped on the Levenspiel plot, and then times XA. So how can I use that to get a volume using a Levenspiel plot? What can I do? And I'll do the same thing. I have this at a certain conversion. How can I use this Levenspiel plot to estimate the volume in a CSTR? So this is a little easier than the PFR case, but it's definitely not as intuitive. So in this case, I'm basically going to multiply the conversion times the flow rate divided by the rate of consumption. But I'm going to do that using the plot. So here I want this particular conversion. I go up to the plot, and then I draw over. And that is how I get my value of flow rate divided by rate of consumption. So the CSTR volume is going to be equal to the area of this rectangle. So to determine that, I basically go to the conversion that I'm interested in, I follow that up to the trend line, and then I follow that over, and I get a value here. And I multiply this value times this value, and that is how I get my CSTR volume. So see, the nice thing about this is if I have a plot for FA naught over the rate of consumption, this makes my life much easier. I don't have to solve a single balance. I can use this graphical technique to determine what the volume of the reactor should be. So considering these two cases, the CSTR volume, which is the rectangle, and the PFR volume, which is the area under the curve, to get the same conversion, which reactor can achieve that at a lower volume? So in this case, the PFR uses a smaller volume to achieve the same conversion. And by the way, I've drawn this, and you probably noticed that I'm not the best artist in the world. But the way this is drawn, the PFR volume is almost half of that required by the CSTR to achieve the same conversion. By corollary, if you have a PFR and a CSTR, which are both the same volume, and you have a Levenspiel plot that looks like the ones we've been working with in this video, which one of those will give the higher conversion? So the PFR will give the higher conversion. So why is that? Why does the PFR, why is it capable of accomplishing a higher conversion for the same volume, or requiring a smaller volume to achieve the same conversion as a CSTR? What is it about the PFR? So think about how the PFR and the CSTR operate. So the PFR, flow rate enters the PFR, it's at some concentration, and then that as the reaction proceeds down the length of the PFR, or down the volume of the PFR, that concentration, the concentration of reactants decreases, and the concentration of products increases. And a CSTR, everything dumps into the CSTR and is well mixed, but the CSTR is operating at the exit concentrations. So the moment everything enters in, it's immediately mixed into this exit conditions, and that's what's being drawn off of the CSTR. So what's happening there? What's happening? So the PFR is maintaining a higher concentration across the reactor than the CSTR. So the CSTR is always operating at the lowest possible concentration, and hence the lowest possible rate, at least in situations where the Levenspiel plot is increasing as a function of XA. And we will get in the next couple of lectures to cases where that is certainly not always the case. But as long as the Levenspiel plot is increasing as a function of XA, then the PFR is going to give a lower volume or a higher conversion because it's operating at a higher concentration. So the rationale, the PFR maintains a higher concentration. And thus a higher rate. The CSTR operates at the lowest possible concentration. So we will practice with these concepts in class or in a synchronous session. There's several questions from the AICHE Concept Warehouse that illustrate these concepts. So if you've gotten to those points, check to see if they have been assigned. Another point to ponder is what I kind of alluded to, which why might the Levenspiel plot decrease with XA? We'll get into that into the next couple of lectures.